We left off here, ready to go through example 4. As always, correct me if I'm wrong. Did you hit your not so funny bone or something?
No, I was smiling at my
Oh, I thought you were like grimacing, like I hit something, you know, like that type of ow. But okay, anyway, sorry. Example 4. We're going to use this same graph several times in a row. Okay, so as we use this graph, be careful how much you write on it, just because it's going to change what it is, if that makes sense. Okay, so as we look at A, suppose the graph shown above is the graph of y equals f of x. So currently it is y equals f of x. That will change, so just be aware. On the interval negative 8 to 8. So if this is the original function, on what interval is the graph increasing and concave up? Thoughts?
-5 to -2.
Okay. Increasing and concave up. And as I do this, I'll erase these pieces probably because, yeah. But yeah, -5 to -2. And we can write this as -5 less than x less than -2. Or you can write it in your interval notation, yes. Either or. Any place else it's increasing and concave up?
4 to 6.
4 less than x less than 6. Okay.
Ellie Taylor, please report to the middle school office. Ellie Taylor, please report to the middle school office. Thank you.
I'm going to keep moving. I'm going to assume that that is making sense unless you stop me and tell me otherwise, okay? B, on what interval is it both decreasing and concave down? What'd you say? Partially disagree. -1 to +2 I can go with. -1 less than x less than 2. Because from -2 to -1 it's still increasing, right? And we need a decreasing and concave down. Any place else? Okay. 3. At what x values does f have inflection points? So inflection points, changing concavity. What are we thinking here? -2. +2. +6. Can you see those? Each of those places is changing from the first one, concave up, then it becomes concave down, then concave down becomes concave up, and concave up becomes concave down. Just helping you recognize the difference in concavities more than anything here, right? Okay. Changing it up, ready to talk about B? Now what is this graph? Now it's a derivative graph. So change your ways of thinking. This is the derivative. That's what we're saying now. So on what open intervals is the function decreasing and justify? So we're being asked the question about f of x, but we're provided the derivative graph. So if we're being asked when the original function is decreasing, what are we looking for on the derivative graph? Yeah. We want when f prime of x is less than 0. So when is my derivative less than 0 here? 2 to 6, because when we're looking for the derivative less than 0, and this is the derivative graph, we basically want below the x-axis, right? So 2 less than x less than 6. My justification is that's when the derivative is less than 0. I'm shorthanded, I don't have a lot of room. Know the y's, okay? 2, at what x value does f have a local max? And justify, of course. So what are we looking at here?
Is it when the slope is zero, so
When it goes from increase to
Okay, so yeah, so in general, mins and maxes on the original graph are the zeros on the derivative, yes? So right here, these 3 points are my derivatives, or are my extrema. Thank you. Mins and maxes. Now, it's only asking, though, for a max. So now what else do we have to consider? When does a max happen? Right? Positive to negative. And so when does my derivative change from positive to negative? At x equals 2, because f prime of x changes positive to negative. Okay. 3. On what open intervals is the function concave down? So when's concave down going to happen?
whenever it's decreasing.
Okay. When the derivative is decreasing. Okay, so I'm going to go ahead and put my justification first. But when f prime of x is decreasing, and what do we mean by decreasing? That's also talking about a negative slope, right? So when the because concavity is the derivative of the derivative. So when do we have this happening? -8 to -5. Any place else? -1 to what? Go all the way to 4. Yep. Inflection points? Inflection points happen when concavity changes, right? So if inflection points happen when concavity changes, we just talked about concavity, like concave down was a decreasing interval, so negative slope. Concave up is going to be increasing, so positive slope. So when are my inflection points then? Mins and maxes, right? And if we think about inflection points, we can think, I really don't have room to write out, but we're looking for places where my second derivative equals 0. Second derivative equals 0 is extrema of the first derivative. Okay, so in that case, then we're looking at three places. At x equals -5, -1, and 4. And those are all places that the second derivative equals 0. And what also has to change? The sign changes, right? So you would also have to make sure that second derivative, I'm just going to simply put changes sign. So we could get specific and say, okay, at -5, it changes from negative to positive. At -1, it changes from positive to negative, you know. I'm just, get the ideas here. Okay, you got it? That's going to change up the graph again. Now what is this graph? Second derivative. So change your thinking up again. This is a second derivative. On what open intervals is the function concave down? When is a graph concave down? When what happens? Second derivative is less than 0. When is my second derivative less than 0 here? 2 to 6. So 2 less than x less than 6. Inflection points. At what x value or values does f of x have an inflection point and justify it? Where is this going to happen? Nobody? Yeah. 2 and 6, because what's happening at 2 and 6? Second derivative changes from positive to negative and negative to positive. So at x equals 2 and 6, and I'm just going to, it's because the second derivative changes signs. Okay, positive to negative or negative to positive. I should be getting more official with those, but I only have limited room. Okay. Example 4D when we're ready. Suppose this graph is the graph of y equals f of x. Okay, so this is, note to self, y equals f of x on the interval -8 to 8. On the same set of axes, sketch and label a possible f prime of x. I guess technically it says in red. It doesn't matter because we're only putting one extra graph on here. So I'm not sure why the coloring is mattering, but so we need to go through and figure out everything we can to sketch the derivative here. Okay? Now, I believe what I did is I set up a number line down here. So we can kind of do a sign chart and talk about what's happening here. Okay. I'm going to put some key numbers that I see being key numbers on here, such as -8 looks key, -5 is key, -2 might be key, -1, 2, maybe 4, 6, and 8. Just anything that could be a key number there, I put on. And so, as we do this, okay, what is our graph doing from -8 to -5? It's doing what? It's decreasing, right? What's decreasing going to mean about our derivative? It's going to mean that our derivative has to be what in this area? Negative. right? Okay. And what is negative 5? Negative 5 is a 0, yes? So just kind of keeping that in mind. What's going on from negative 5 to negative 2? It's increasing. If you want to go ahead and mark it, negative 2 is a what? Point of inflection. And this is me just gathering information. I'll turn it into derivative information here in a moment. From negative 2 to negative 1, my graph is still increasing. We could talk about the fact that negative 1 is a what? Max. I guess back here at negative 5, besides being a 0, it was also a minimum, right? From negative 1 to 2, my graph is decreasing. 2 is also a 0. From 2 to 4, my graph is decreasing. At 4, I have a minimum. From 4 to 6, my graph is increasing. At 6, I have a 0. And 6 to 8, my graph is increasing. To each their own. You'll figure out your ways you want to do this. Is this all necessary? I don't know. To me, it's helpful to keep it all sorted out. Now, I want to go through what I was doing here. So, like what I started here. This decreasing interval means my derivative is negative, yes? So then I'm going to have a positive derivative, negative, negative, positive, positive. So that's just kind of the idea of what my derivative is doing there. And I'm trying to think what else I need to talk about here. We can also talk about concavity a little bit, because concavity will help here. Okay. So let's go through and talk concavity, and then we'll talk about what that means for first derivative. So from negative 8 to negative 5, what is my graph in terms of concavity? That's concave up, yes? Negative 5 to negative 2, concave up. Negative 2 to negative 1, concave down. Negative 1 to 2, concave down. 2 to 4 and 4 to 6, both concave up. 6 to 8, concave down. Now I'm going to go back. That's just me purely taking the information off the graph. Are we okay with that, I assume? Please always tell me if I assume wrong. Okay. So now, gosh. So when we talk about a derivative here, if a graph is concave up, what would that have meant about the slope of the first derivative? The slope of the first derivative would have been what? Positive. So the idea is that the derivative is increasing in that. It's going to be a negative value. So negative value meaning it's going to be below the x-axis, but it's increasing. Okay? Yes?
Why is 6 to 8 concave?
Right here?
No. The derivative, or the second derivative. Yes.
This right here?
Yeah.
Okay, so this, the second derivative, well, okay. Second derivative tells us about concavity. This is the original graph, the f of x, and the original graph is concave down.
Okay.
Does that make sense there? Okay, so the original graph was concave down. So in terms of that being concave down, I mean, I guess what it's saying here is that since this is concave down, my second derivative would be negative. So I guess I'm not saying, don't interpret that as me saying the second derivative is concave down or concave up. Does that make sense? Is that what okay. Okay, so -5 to -2. Since this is concave up, that also means that my first derivative is increasing. Between -2 and -1. Concave down means my derivative is decreasing. -1 to 2, decreasing. 2 to 4, increasing. 4 to 6, increasing, because those are concave ups. Concave down, decreasing. And what I'm trying to do there in the red, that's what we're getting ready to put on the graph. That's what I'm attempting to do here. Now, it does not give me a starting point, does it?
So why are the first arrows?
You're welcome.
Why are the first? Like, why do they have two separate arrows?
So my blue arrows versus my red arrows.
Yeah.
Okay. And so in the blue, what I was doing is giving information based on the original graph. And so the original graph, like, so from here, it was decreasing. Then it was increasing. Decreasing, decreasing. So that's what this was. That was just information there. Those arrows defined, okay, is my derivative going to be negative or positive? So because my original function is decreasing here, I know my derivative will be negative below the x-axis. Here, because the original function was increasing, positive slope, my derivative is going to be positive above the x-axis. Whereas the other arrows have to do with concavity. Because the original function was concave up, well, when it's concave up, second derivative says, okay, concave up, positive second derivative. Positive second derivative would be a positive slope on the first derivative. Concave up is going positive.
Positive slope, like on the negative side of the graph.
Yes. Yes. I know. There's a lot to take in here. I know. Trust me. And me trying to get this to you guys is a lot. So we're going to do what we can here. Okay. Okay, we're ready to try this? I'm trying to think. Do we have all the information we need? Probably the only other thing, what do we need to talk about? On the original function, okay, max and mins on the original function. What are those going to be on the derivative? Zeros, right? Okay, so like here, because there's a max, that's going to be a 0. There's a min here. Guess what? It's also going to be a 0, and over here, there's going to be a min.
Where do the POIs go?
What?
Where do the functions?
Good question. Okay, so let's see. 0, 0. I guess I probably don't need to put it down there, but 0. Okay, point of inflections. So point of inflections are critical points of the second derivative, right? So that means they are zeros on the second derivative. Zeros on the second derivative are going to become what on the first derivative? Mins and maxes. Okay, so like here, we have an inflection point. That's going to be a min or a max. Now, if you look, because it's increasing and then decreasing, that's going to be a max. And I don't necessarily have, I mean, you know, we can put a dot here somewhere. We don't necessarily know where, but that's going to be a max of some sort. What else? This inflection point. Notice it's going to be decreasing to it, increasing to it. So this inflection point is going to be a minimum. Okay? It's going to be a minimum of somewhere. And 6, it's increasing to 6 and decreasing away from it. So 6 is going to be a max. And these mins and max dots, is this where they have to be? No, I am arbitrarily putting a dot either up high or down low. Okay? This is a sketch. This is not precise because we don't have any actual values. Ready to try it then? Hey Matt, why did I put a max at -2? Because as I look right here, around on either side of -2, that was me hitting the button over here. Okay. As I look at either side of -2, we're going to have we've already decided that our derivative is going to be increasing and then decreasing here. So if I'm increasing, that's how I was easily looking. Or going from positive to negative. Okay?
What are the requirements for a
Point of inflection is when the second derivative equals 0 and the concavity changes at that point. So your second derivative sign changes from positive to negative or vice versa. Okay? Okay. Are we ready? Because we know we're increasing here and I have to cross through here, I'm going to start down here. I'm picking an arbitrary point, guys. And as we do this, it is below the x-axis and it needs to be increasing. Now, do we know concavity? How do I know concavity? Okay, my brain just went blank.
Yes.
How about, it's that comment right there that I have written up. Okay, so as we do this, let me write this in, then we'll talk about it. Concave up. Sorry, that worked out weird. Concave up is when we have an increasing first derivative. Concave down. Wait, is this going to do it for me? Sorry, I had this all figured out last night, and now my brain's... Or no, does that... Okay, I think I got it. So the idea here, from first point to second point, my graph is decreasing, yes? Decreasing here means my derivative is going to be concave down. So as I start from here, and I'm hitting this point right here, it's going to be concave down. So that is a curve, curve down.
I thought it was concave up.
The original graph was concave up. Okay, that was just trying to get whether my graph is going to be, my derivative is going to be increasing or decreasing. Okay. From -5 to -2, this graph is increasing. So my derivative is going to be concave up. Okay. And that was supposed to be a max there, right? Now, from -2 to -1, -1 is a 0 here. I already have that point. My graph is what? Increasing still? So increasing is going to be concave up, which means this is going to make it a hard point because it's going to be slightly concave up. -1 to 2. From -1 to 2, my graph is decreasing, decreasing. Should be concave down. Why do I not have my graph concave down? Why do I not have my graph concave down?
I don't know this.
I don't.
I had this all straightened out, and now put me in front of you guys, and I'm struggling.
I'm so excited.
That was today.
It's lab day. No, yesterday you said it yesterday.
It's a really truly lab day, though.
Yes,
So
it
my day
actually
actually
is.
is.
We talked about how
It made me
excited
excited. He told us
Yeah,
yesterday that today should be
anymore.
a lab day.
No, he said Tuesday or Wednesday. Today is Tuesday. Or Wednesday.
No, but when I went back and asked him, I said, so we have lab day tomorrow. He said, yeah.
That day.
No, lab day just isn't the same.
It's so hard.
Because it makes you feel so stupid and you can't get the
I
answer.
know, I miss the old
Yeah.
lab day.
I missed like the first 2 labs.
Those ones are actually fun.
And then it's just, I'm
We
just.
still don't have our labs. I just want to go home.
Oh,
You know, I can't even go home after school because I don't have my car.
So,
Take it home.
one, 3 vehicles.
I don't even know if I can.
That's what it
I can't even think of it.
They're due like pretty frank. You get like that.
And then we can have more now.
You act so
No,
confused.
Just want to take the children home. and then
Because I
mine
got the
house.
first one that we have everything. It's just not.
Is there gonna be
It's not
two
gonna-
kids?
See, like, I don't like writing directly.
I just want to make sure that it's not scribbled pictures first. We can't. I think I'll try to find it down there. Once I'm done.
This is so.
What am I doing wrong? Okay, guys, I'm not sure what I'm doing wrong, and it's driving me crazy. I know it's going to drive you guys crazier. I have the rest of this drawn. Concave up, concave up, concave down.
Did you draw it to accidentally match the other graph?
I don't know what I did. That's what... This is what I have it drawn as. I'm trying to... We know concavity, right? Do we not?
I don't.
I know, you guys don't know.
Isn't the slope decreasing
Yeah, that's what.
from -1 to 2? Yeah. So shouldn't it just be? Oh, that's the problem.
Yeah, that's what she's at.
And I had this all worked out in my brain last night, or 2 nights ago, and now it's not working for me.
So is that what she did?
Oh, then it does.
And that's what I just pulled up my iPad to see.
So it should like match the graph. It should have matched. Yeah.
Well, it gets funky in other places too.
Yeah,
Okay,
like it looks like to me it just matches the graph.
I'm gonna have to sit back down and look at this because it's not.
Incomplete.
Something is not clicking with my brain right now, and I'm not sure what it is. And all I can do is apologize here, because it is rough. It's rough when your teacher gets lost, right?
I'm excited for the
There is a-
Wait, wasn't that yesterday's thing?
Okay.
She can't handle it.
I can't right now.
I just noticed it.
Okay. Here's my best suggestion. I need a break from this problem because it's not working. It's frustrating me.
You don't know what to do, you just skip it. That's what I do.
Okay, well, I'm going to be the student here. I'm going to skip it. And because I'm struggling with this, I probably shouldn't try and teach E right now.
No.
So let's go on to the next page.
I was looking at that.
Perfect.
Sounds like a
Great
plan.
to me.
I need to do something to give you guys some confidence walking out of here, right? Regain my confidence, maybe. So we're skipping to 5. I don't know what I'm doing there. I don't know. Okay, on 5. I didn't put what you guys have at the top of your notes there. Because you have it in your notes, you can read the notes. But it gives guidelines for analyzing the graph of a function. Okay? It's basic, what you guys already do. We're going to talk about domain, intercepts, asymptotes, symmetry, just basic what you know based on looking at the equation. We're going to talk about critical points, so that's going to be first derivative, increasing, decreasing. We're going to talk about max and min then, there's your critical points. We'll talk about second derivative, concavity, inflection points. A through G kind of walk us through it on this one. Okay. So, now, I actually want to start with, well, no, we'll get it there. So, X and Y intercepts. Revert to pre-calc, revert to algebra 2. Where do X and Y intercepts happen? When the other variable equals 0, right? So, for instance, when do x-intercepts happen? Well, x-intercepts are another word for zeros. So x-intercepts happen when y is 0, right? So the idea of x plus 2 times x minus 1 squared equal to 0, that was a weird 0. Then you guys know that's the idea of set each factor equal to 0, right? And so we're going to have x-intercepts at x equals -2 and 1, correct? We can do that. Yeah, that's algebra technically, but we can do it. Okay, where do y-intercepts happen? Y-intercepts are going to happen when x equals 0. So if we look at that one, that's putting 0 plus 2, 0 minus 1 quantity squared. And so we're going to have a y-intercept at what? 2. And if you want to go ahead and jump down, can we go ahead and put those points on our graph? Because when we get down to G, it's going to be sketch the graph. So x-intercepts of -2 and 1, y-intercept of 2. Okay, there's something for you. Okay, B says find the first and second derivatives. Okay, meet me at the end. You know what to do here. Well, okay, I say that. We have options here, I guess, on how we can find first derivative, don't we? In all honesty, my recommendation is to multiply that out. Or you can do product rule. I don't honestly know which is better. I mean, I think it'll work out the same either way. So when I look at my notes, what I did off to the side is I multiplied this out first, and then I did my derivatives. Ethan, if you want to do product rule and meet me, that'll work too. We'll get there. Okay. So x plus 2, when I square x minus 1, FOIL it, is x squared minus 2x plus 1. Then when I multiply, x cubed minus 2x squared plus x plus 2x squared minus 4x plus 2. If I clean this up, x cubed minus 3x plus 2 is another form of the function, yes? and then I can do derivative. If you did product rule, it should work. So if we look at my original function, g prime of x, so the derivative is going to be 3x squared minus 3. And it doesn't say it here, but I would go ahead and find your critical points right here. Okay. So if I find critical points, that's going to be setting my derivative equal to 0. What can I do with 3x squared minus 3? I factor out a 3. I have 3 times x squared minus 1 equals 0. And if you want, that factors into x plus 1 and x minus 1. Or maybe you didn't factor in, you just went ahead and said equal to 0 there. But we're going to have critical points at 1 and negative 1, correct? No?
How does that x squared minus 1 factor out?
Difference of squares. You need to go back and sit in Algebra 2 for a day.
Yeah.
We're doing lots of factoring right now. Okay. Second derivative. Second derivative of 3x squared minus 3 is going to be 6x. If I set that equal to 0, we're going to have a second derivative critical point of x equals 0, correct? Okay. C. So complete a sign chart for g prime. First derivative to find the intervals where g is increasing or decreasing. First derivative. So what are my critical values I need on my first derivative? Negative 1 and 1, yes. And we're going to take those, we're going to figure out increasing and decreasing there. I would plug in here, or you can plug in here, either or. So to the left of negative 1, positive. I actually ended up plugging in right here because negative 2 was 4 minus 1, that's 3, that's positive. And between negative 1 and 1 is, I plug in 0 and I'm going to get a negative. To the right of 1, if I plug in 2, I'm going to get a positive. Positive first derivative indicates increasing. Negative first derivative indicates decreasing. And so for my increasing intervals, I have negative infinity and negative 1 and 1 to infinity. For my decreasing interval, I have negative 1 to 1. We're okay with this stuff, right? Okay. Tell me.
Is this saying like it's going to be on the negative side of the graph, or is it's saying this is what the slope is doing?
Increasing, decreasing is what the slope's doing. So our original function is going to be, because our derivative was positive, negative, positive, our graph is going to be increasing, decreasing, increasing. So like this right here is your first derivative. This down here then is what the original function is doing. Okay?
What determines like if it's on the negative side? You know how last time we
Positive versus positive or negative. Okay? And that's more if you're looking at a derivative graph, trying to talk about the original.
Oh.
Okay? And we're just going to be drawing the original graph here. Okay. Determine any relative extrema. What do we know? What's going to happen at negative 1? Yeah, we're going to have some type of relative max at negative 1 comma something. It would be helpful to have that ordered pair, so plug in. And I'm going back to the original right here. Looks like it's 4. At 1, I'm going to have a min, right? And I'm just looking right back here at my sign chart. I can tell that's a max. I can tell that's a min. So I'm going to have a min at 1 comma something. At 1, 0. Which 1, 0 was already one of my x-intercepts, wasn't it? Okay. E, complete a sign chart for concavity. Second derivative. Okay, if we're talking about a sign chart for the second derivative, what was my critical value of the second derivative? It was 0. So I'm putting 0 on my line. What is my derivative doing to the left of 0? Well, my derivative is 6x. To the left of 0, it's going to be negative. If I plug in a positive, it's going to be positive. So that means where my second derivative is negative, the graph itself is going to be concave down. When my second derivative is positive, the graph itself is going to be concave up. Yep, and that's what part F asks, which is, so concave down interval is negative infinity to 0. Concave up interval is 0 to infinity. Since my concavity changes at x equals 0, points of inflection. There's a point of inflection at 0 comma something. And that's because the concavity changes. When I plug 0 into my original, did I already have 0? We already have 0 plugged in at some point, don't we? Well, okay, it's our y-intercept. That's what it was. I'm like, I know I've done this somewhere. Okay, so these red points I already have on here were just points on the graph. Okay, those were the x and y intercepts. Then let's put our max is at negative 1, 4. So that's a max. We have a min at 1, 0. So we have a min right there. So max and min. We have an inflection point at 0, 2, which is already one of our pieces. My graph is going to increase from negative infinity to negative 1, so it's going to increase to that max. It's going to decrease from the max to the min, and it's going to increase after the min. Concavity, it's concave down on the left side of the graph. It's concave up on the right side of the graph. Are you visualizing what this is? Yes? No? I'm increasing, decreasing, increasing, concave down, concave up. It's all there. I'm trying to pick one out of the 4 problems we have left. Take that aggravation myself, by the way. Just saying, don't take it on yourself. Take it on me. Okay. Let's go to example 8. I don't know if I can get done in 5 minutes, but, you know.
We're going to try.
We're going to do what we can here. Okay, now, before we proceed, there's a typo here. This 2 is supposed to be a 2. It's a 0. I was really confused trying to do this problem because I could not get that to work out until I looked back at the originals. So, okay. H is a function continuous over the interval 0 to 6, twice differentiable, except at x equals 3. So if it's not differentiable there, what are we likely seeing? Some point that is a cusp, a hard point. Could be something like an asymptote, but it said it's continuous, right? So my brain automatically went to thinking cusp, hard point, sharp point. Do I know that for sure? No, but likely something like that, because it says the derivative does not exist. The function and its derivative have the properties indicated. Use the table to sketch. Okay, so we have all this information. First of all, we have some points here, yes? When x is 0, h is 3. What's that going to tell me on my graph? I have a point at 0, 3. I have a point at 2, 0. I have a point at 3, negative 3. And I have a point at 5, 0. Easy enough? Okay. What does my first derivative say about my function? My first derivative tells me whether my graph is either increasing or decreasing, right? So here, in between 0 and 2, my derivative is negative. So what's my graph going to be doing? Decreasing. Then between 2 and 3, my derivative is also negative, so my graph is also going to be decreasing. Positive derivative means my graph is going to be increasing. Positive derivative, my graph is increasing. Now look, does that make sense? Does it make sense that we would decrease, decrease, increase, increase? Okay, connect the dots kind of, right? What's second derivative tell me? Concavity. Negative means it's going to be concave down. Positive means it's going to be concave up. Concave down and concave up. Okay. Now, in between concavities, positive to negative concavity, this is a 0 here, so this means it is a point of inflection. This one doesn't exist. That's that cusp, right? And then this one, the reason it was so important that it was a 0 in my brain is because it's also a point of inflection. If it's not a 0, though, it can't be a point of inflection. So that's where my confusion was. Okay. So, and then decreasing, that's not a min or a max, and those are both increasing, so not there. Okay, so from my first point to my second point, my graph is decreasing and concave down. So something like that. From 2 to 3, my graph is still decreasing, but this time it's concave up. There's a slight change there, I promise. Next piece, increasing but concave down. And the final piece, increasing but concave up. And I don't have an ending point, so I just drew it off there to the side. That was a good 5-minute problem. I picked wisely there. I found something we could do. Okay.
It's okay. You can't be the best teacher every day.
Hey, I'm owning up. That was a horrible day for me.
It's all good.
Woo.
You don't have to.
Well, I'm gonna say do what you can with homework. I don't know what to say other than that. I don't know.